Hello everyone. So today we are going to learn about analysis of algorithm. So analysis of algorithm is a very important topic before you dive deep into data structures and algorithms. Alright. So let me first tell you like why it is so important, why it is needed. So there are like many problems which have a number of solutions. And as a software engineer, your task is to find the algorithm which will solve the problem in the least time, which will be more efficient. All right. So to find out, to compare between algorithms, we use analysis of algorithms. All right. So in computer science, we use asymptotic analysis. So what asymptotic analysis does, it measures order of growth of time taken by a functional program in terms of input size. Okay, for example, suppose input size is n. So it will tell how the program grows, whether it grows quadratically, linearly, constant, etc. Alright. Okay, let me give you an example. So here we have a question, find sum of first and natural numbers. Suppose we have given this question to two software engineers, alright. So one software engineer came with this solution and one software engineer came with this solution. So let's see here what he did. He declared a variable sum and then he put the value of sum as n into n plus 1 by 2. This is a standard formula for finding sum of first and natural numbers and I hope you must be knowing about it. And this is another program written by another developer, and here what he did, he declared sum, alright, and then he used a loop which ran from I is equal to 1 till n, and he added the value of iterators 1 plus 2 plus 3 and so on. Okay, and then he also returned the sum. So now let's talk about time this program takes. So what this program does is it adds two numbers, multiplies two numbers and divide two numbers. So operations such as divide, subtract, add, multiply, they takes constant time. Alright, nothing else, just constant time. So here, what would be the time taken then? Constant. So I'm saying C1. C1 is a constant. Alright, any constant. And let's come to here, program 2. Now looking at this loop, sum is equal to simplify. This statement takes constant time. Suppose it's taking constant time of C2. Alright. And it is run for n number of times. So it is like C2 plus C2 plus C2 C2. Alright. And this is, n times. Right? So it would be what? NC2. Alright. So time taken here would be what? NC2. And then there will be some other things in this program which would be taking constant time, such as declaration of variables. For example, declaration of variable of sum, declaration of variable I. So we can say they are taking C3. Alright. So this is what we do here. Now in asymptotic analysis, you will come across asymptotic notations, which includes big O of n, theta of n, and I'm sure you must have heard these somewhere. So we'll study them under this asymptotic analysis. Okay, but before studying them, let's talk about order of growth. We'll talk about order of growth in more detail. Alright, let's talk about order of growth in more detail. So, as a software engineer, what is our main task? You've been given a problem and there would be multiple solutions of the same problem. Now what you have to do is to find the most efficient solution which takes the least time. So what you will do is you will find time taken by all the algorithms. Alright. And then you'll write a polynomial in terms of time, and then we see order of growth of every time taken, you know, and one having least order of growth, that algorithm becomes efficient. Okay, and now you might be wondering what is least order of growth, what might be the higher order growth. So basically you might be wondering how to compare order of growth between two two polynomials. All right, so let me tell you how we can do it. Suppose there is a function of time fn, all right, and there is a function gn. So a function fn is said to be growing faster than gn if gn upon fn is equal to 0 when n tends to infinity. All right, so it means that gn has a higher order of growth, and gn having lower order of growth. All right, let's take an example, you will understand better. So here, see, fn is equal to n square plus n plus 6, and gn is equal to 2n plus 5. All right, so what we'll do is we will put gn here, gn we have put here 2n plus 5, right, and fn is here, and we have to put limit n tends to infinity. And I'm hoping you guys know how to put limits. This is basic maths. So what we'll do, we'll divide numerator and denominator both by n square. All right, so this becomes 2 by n, this becomes 5 plus n, 5 by n square, 1 plus 1 by n plus 6 by n square. Now as we put n is equal to infinity, these terms become 0. So this becomes 0, this becomes 0, this becomes 0, and this becomes 0. So final result becomes 0. Hence you can say this gn function has lower order of growth, and this fn function has higher order of growth. But when comparing many order of growth, you will not do every time, you'll not do limits. So there has to be a simpler direct way to find order of growth. All right, so yeah, there is one, so we'll talk about it. All right, so we'll talk about now direct ways to find and compare growths. All right, so it involves two steps. First we have to ignore lower order terms, and then we have to ignore the leading terms constant. Okay, so yeah, leading terms constant. All right, let's talk with an example. See, fn here is 2n square plus n plus 6, right? Now what we have written here, ignore lower order terms. So what are the lower order terms? N plus 6. So we'll ignore this, ignore this. Now this is the leading term, and what we have written, ignore leading terms constant. So 2 has to be ignored. Now what we are left with, n square. Hence order of growth of this function becomes n square. Now let's talk about another function, gn. Alright, here also what we have written, ignore lower order terms. So we'll ignore this term, we'll ignore this term 3, and then we'll ignore leading terms constant, which is 100. So what remains, n. So order of growth of gn becomes n. Now we have got order of growth of two functions. Alright, now how do we compare them? So we have a small hierarchy which is very easy, and you can learn it very easily. So it involves like this. So the least order growth is with constant. Alright, constant grows with the least order. Alright, basically constant doesn't grow, obviously, right? But still we have put it in the hierarchy table because we have to compare it with other terms. Then after that, log of n, it grows, very minutely. And then there is log n, which grows faster than log n, and this continues. This is n 1 by 3 and a cube root of n. This is square root of n 1 by 2. This is n. This is n square, n cube, n raised to power 4, 2n, and this goes on. Right? Then n power 5, n power 6, and so on. So let's come back to our example. Alright, we have Fn, we have order of growth n square, and Gn, we have order of growth n. Alright, now what? C, where is n square? Here, right? N square is here, and where is Gn? Order of growth of Gn is n, so n is here. So as you can see, n is smaller than n square in this hierarchy table. So we can say that Gn's order of growth is less than Fn's order of growth. So suppose there is a function, there is an question which have two algorithms. One whose time polynomial is Fn, and another algorithm whose polynomial is Gn. All right. So order of growth of Fn is n square and order of growth of Gn is n. So we'll say that the second algorithm of Gn would be more efficient because its order of growth is less than that of Fn. So this is how we compare different algorithms. Alright. So I'll end the lecture here, and in the next video we'll learn about asymptotic notations, which will include big O of n, theta of n, and then we'll cover like what can be the best and worst time complexities. Alright. So see you next